Alright, here are the pivots for the wing. It's basically two halves, and then I put some polyurethane O-ring material in here to act as bumpers. So this would be the bottom half, and we have to attach counterweights. So what I do there is there's a hole through the front. The bolt goes on there, and then a nut goes on here. This is a nylock nut, and then I just thread that all the way down. And then after that I add another nut and some washers and another nut, and that way the counterweight can be adjusted forward and back as needed. And then the top goes on, and there'll be a piece of this kind of craft foam in here, and that will go like that. And so that will pinch on the wing itself without crushing the wing, and it will just hold it in place when this gets tightened down. So there'll be some number 6 nylock nuts that go on the bottom here, and hold that all together. Okay, I have a 5mm flanged bearing in the arm, and I'm going to attach half the wing holder using this clevis pin, a couple 5mm washers on either side of the bearing, and then a cotter pin to hold it all together. Okay, so all the pivots are in place. Now I just have to install the wings. There are 3 important parameters for designing a Sharp VAWT. There's more parameters, but these are 3 more specific to Sharp VAWTs. One is how fast the wings pivot. You want to make sure that in there, just for like a natural frequency of the wing, it can pivot quickly enough so that it can adjust in time. So I do a test where I just hang it sideways, check the natural frequency of the wing, and I ran the test and found that the wing could pivot one cycle in 0.6 seconds. I do that just by counting video frames, and that's how I measure the oscillation period. Then we compare that with how fast the wind turbine would be spinning when it's generating 1 G at the wing tips. So the acceleration is r omega squared. So 1 G is 9.81 meters per second squared. The radius is 0.6 meters. And then just solve for omega. You get 4.04 radians per second. Convert that to revolutions per second. And then if you just take the inverse of that, get 1.56 seconds per revolution. So when the turbine is spinning 1 revolution every 1.56 seconds, it will be generating 1 G of acceleration at the tip. So we see that the wings are able to adjust, about twice as fast as the spinning of the turbine. So that turned out pretty good. And that's why I favor smaller wings instead of like 3 large wings. So I went with 5 smaller wings to try to make sure this is down low so that it can pivot fast enough. The other thing is the ratio of inertial and aerodynamic forces. I have this Bosch number I came up with, just a dimensionless number. You got mass in the numerator, fluid density, and turbine radius, and wing area in the denominator, and I get 4.7. I look for something around 3 to 3.5. That's a little bit high, but it's not bad. I've seen numbers as high as 30 or so when this radius gets pretty small, and it still functions. It's just that if this number is very large, it behaves like the wing is fixed, and you get a fairly high angle of attack. If this number were very low, your wing would, the aerodynamic forces would dominate, and it would tend to weather vane into the wind, and you wouldn't get as much much angle of attack, and so you wouldn't get as much lift. So this is a pretty good number. And then the last thing that's kind of unique for a Sharp VAWT is you have to balance the wings. Okay, here I have a piece of metal fence, something or other, and I've got it clamped to the table, and then I slid the tube over that so that this thing is sitting sideways. Okay, here's a simple test, but I got to do it to make sure that the blades are responsive enough. So I'm just seeing how fast they oscillate just on their own. And then what we can do is we can compare the rate of oscillation with how fast the wind turbine is spinning and when it produces 1 G of acceleration at the end of the arms. I have the wing and the pivoting hardware on a scale, and we're reading 291 grams. Just earlier it was 292, it just drifted down. But anyhow, if we do the Bosch number here, there's mass divided by density of air divided by the radius of the turbine divided by the area of the wing. So it's inertial forces over aerodynamic forces. So we got 0.292 kilograms, well it's 291 now, but divided by 1.2, that's density of air, 0.6 meters is the radius of our turbine, chord is 0.072, the length of the wing is 1.2 meters, so we get a number of 4.7. Okay, these weights are just loosely retained here. And I've got this arm approximately vertical. It's not critical, just got to make sure there's room to pivot here. And then the idea is to make this level. So I'm just going to measure from the floor to the tip or the leading edge, and then I'll measure from the floor to the trailing edge, and then just adjust the weights so that this thing is level. So that's just a little under 3.5. It's just slightly, or right around 3.5. So I want the tail end up a little bit, so I'll just move the weights a little bit outward. That one looks, the far one here, looks like it's a little bit out farther than this one, so I'll just leave that where it's at. And then just loosen this a little bit, slide the weights out, and snug it up a little so that they're where they should be. And then just check and just keep adjusting until it's all there. Okay, so that's like 3 3/8 or so. That's about the same. So this, I'll give it another check and then I'll make sure it's level. But that's pretty much the procedure. Just keep adjusting the weights until the leading edge and the trailing edge are at the same height. It's not bad if the trailing edge is just slightly higher. That's always good too. But not much. It should be pretty close. And then I'll just do that for all 5 wings, and then it will be balanced. Alright, here's the spindle again. We had a video about this earlier, but just wanted to refresh your memory. I've got to put the turbine on top of that, and I've got to walk it all the way from the shed, climb up this ladder, put it on there, and there's a little bit of a breeze, so this is going to be the most challenging part. Okay, it's installed. It was a little bit easier than I thought it was going to be. The nuts are on there. I have to go get my metric wrench and tighten them up, but they're up. There's a light wind, and it was actually starting to turn this thing, so I'm encouraged. So I'm going to go get the wrench, tighten it down, and then We'll see what happens when we get a little wind. The banging you can hear is when it just when the wings are hitting their stops, just when it's starting up. But once it gets spinning, it quiets down. It looks pretty nice.